We'll probably get an especially slow trickle of people showing up. But let's go ahead and begin. Again, these last few lectures, each one of them, it's very difficult to express just how amazing these are, because these, more than anything else, these ideas, particularly today and next week with quantum mechanics, these ideas emerged in the early 20th century and changed everything. I mean, they ushered us into the modern era. If we were to draw a line to say, okay, this was where the Enlightenment ends and modern time begins, modern technology, modern era, this is it, where these ideas emerged. This is 1905 to 1915, the point from which Einstein developed the theory of special relativity to the theory of general relativity. At the same time, the quantum physicists are devising the theory of quantum mechanics, and so we're going to look at that next week. But right now I want to focus on relativity. And I want to go back to where it all began. As we said, this course tries to focus on things from this way. How did this understanding emerge in our consciousness, not only in the scientists' minds themselves, but in all of humanity's consciousness. And so I put this up here. It all starts with the night sky, right? Go way back, before any science or technology, any of this. We look up at the night sky and we wonder, wow, that's really beautiful. It's astounding. There are stars that fill the sky every night, and they move. They change. During the night, throughout the seasons, throughout the year, we see the night sky change. And it appears to move. So the assumption early on was that it's the stars that are moving and not the Earth. The Earth feels like it's still, and it looks like the stars are moving. And we even get a sense almost of the motion being that the sky is moving, not us. The knowledge that it's the Earth that's moving took a long time, because it takes very meticulous observation to really realize that the patterns of motion that we see in the night sky can really only be explained by the Earth rotating on its axis. And this took, again, if you remember to David Deutsch's talk about how mythology was replaced by better explanation, and all of those kinds of things, how long it took something like the Enlightenment for people to take a second look. Early in the Enlightenment. This is some of the stuff that began the Enlightenment. This sort of is what started the whole process of looking at the natural world in a different way. Because we realized, again, the more carefully we looked at things, that old explanations didn't satisfy. We couldn't really explain everything we saw with the model of the Earth staying still and the heavens moving around it in some kind of celestial sphere. It only worked mathematically and to fit all of the observations that were made by Copernicus and others, that it's the Earth that's rotating, and it's the Earth that's revolving around the sun. This made no sense, though, to most people, right? I mean, it seems to violate everything we see. So in many ways, this was also the beginning of how science has helped us realize that our senses oftentimes aren't as trustworthy as our intelligence. That we have to impose some kind of method on our observations to interpret what we see in the proper way. This was a change in the way we see the world, the way we think about ourselves, the way that we explain things, and it all started happening very fast. And I'm not going to go into the political history, the history of the reaction of the Catholic Church, for instance, to these ideas. Obviously, if you study any of these, we'll talk about Galileo, and there's a lot of very interesting history in that aspect as well, because things were changing so fast, and these ideas were so challenging to the way we have accepted things previously, that it really did cause a lot of turmoil, a lot of upheaval in society. I put Kepler here instead of Copernicus in the picture because I want to mention both of these scientists, at least a little bit, very briefly, because of their role in taking the Earth out of the center of the universe, out of the center even of our solar system, putting it in orbit around the sun with the other planets. And again, it was careful observation of these planets' orbits and other constellations moving through the night sky that led to, first we had to recognize the planets as opposed to just stars, other stars, had to differentiate between those. Galileo, again, was around at the same time, other scientists making observations, distinguishing, hey look, these bright lights in the night sky are different. And in fact, if we look at them more closely with our new instruments, we can see that they're planets. So again, these startling observations, but also required explanation of why are the planets moving the way they are. Copernicus and Kepler provided the actual model that we sort of still use today of the planets orbiting and doing the mathematics behind it that sort of gave us this somewhat clockwork universe that could be described by physics, by physical laws, including gravity and the laws of motion. This set all that thinking in motion. How do we explain this? How do we explain that the planets are moving? What's making the planets move? Is something in between the planets affecting their motion, causing them to move? We're going to ask this question. It's going to become a very fundamental question. Is all motion relative, or can some things move, can there be motion without something to compare it to? And we brought this up before because we've talked about our own sense of relativity. That here we are sitting in this room, relative to each other, we're at rest. Relative to the sun, we're moving. Relative to other things, we're moving. We have to be aware of those other things to know that we're moving. We don't feel like we're moving because we're moving along with the Earth. The Earth is spinning. We're not aware of that because we're also spinning with it. So there's no relative difference between our motion and the Earth's, right? We're revolving around the sun along with the Earth, so we're not aware of that motion. We only become aware of it when we realize that the position of the sun through the night sky or the position of the constellations in the night sky show that we're moving relative to those objects. So the question was, if you didn't have something to compare your motion to, how would you know you're moving? Is there any way to determine that we're moving without something to compare our motion to, a relative object? This is where the term relativity sort of comes from. And it was very obvious to Copernicus and Kepler and Galileo and Newton and all these early scientists, and even philosophers like Descartes, that we had to explain motion. We had to be able to explain motion either as an absolute state of being. In other words, things can be moving in a vacuum without something to moving them, or everything is relative. Everything is moving relative to something else. Now, there was a debate going on, and we're going to see how this grows into our modern understanding of things. And it was a somewhat philosophical debate at first. As a matter of fact, that's why Descartes up here, he was the one who sort of suggested that all motion is relative. That, you have to have something to compare motion to, or else it's not moving. Newton disagreed. He believed that there was absolute motion. Again, Galileo, I put him up here because he sort of established the first rules of motion. Newton followed up with his laws of motion. We've studied those laws. This is classical physics. In Newton's laws, all motion is relative. But he believed that if you extended this out into the universe, there are situations where things can be moving without anything to compare them to. And he used this bucket as an example. So let me try to explain this a little bit. The bucket problem. It's not a bucket list. It's a bucket problem. Okay? So what he said was, if you take a bucket of water and you spin it, initially it starts spinning and you don't see any change in the surface. The water is moving relative to the pail. And you don't see any difference, you wouldn't measure any difference in motion because the pail is spinning and so is the water. The surface of the water is flat until it starts to spin fast enough, and then you notice that the surface of the water becomes concave. It changes in shape. So you could see that change in shape even if you couldn't see the bucket. Even if the bucket and the rope are invisible, you're out there, in space. There's nothing to see around you, but you notice a change in the shape of the curve of the water. That would prove that it's moving, even though there's nothing to compare this motion to. Okay? And that was Newton's argument. Now, Ernst Mach disagreed, so I put him up here. And this is the scientist who we named the speed of light, or how the measure of speed of light of sound to Mach 5, right? That's where that term comes from, the scientist's name. And he studied sound. He measured the speed of sound. He measured sound waves, and he realized that all these waves, these sound waves, have to move through something. And so he argued that there is no absolute motion, it's all relative, because there has to be something through which the energy moves that causes these motions to take place. And this debate raged on for quite a long time. And we're going to see how some aspects of both their arguments were true. And it sort of came down to how we explain light. So as we just mentioned, as Mach figured out that sound travels through something, that kind of wave was the earliest kind of wave that could be studied. If you remember, we had primary waves, secondary waves. These are the primary waves, the transverse waves, that travel through a medium as vibrations, like my voice is traveling through the air. But if you look at light, it wasn't as obvious that it traveled the same way. If you studied it as a wave, you could measure certain properties of light, but there were other properties of light that made it seem to be more like a particle, traveling as a particle. Even Newton described light as particles, which may surprise you because we think of this as a modern idea. This is where we're getting to, Max Planck and Einstein and others, who proved the particulate nature of light. But it wasn't a new idea. It had just gone back and forth between scientists arguing whether or not light was a particle or a wave. And it seemed like it had to be one or the other, because everything else we observe is one or the other, right? Sound is not a particle, it's just energy. It's just moving through heat, too. Thermal energy, passed from molecule to molecule, but it isn't passed by a particle. So that's what we knew, and light was the challenge. As a matter of fact, light was such a challenge as we learned more about it that we had to invent something that light could move through. And again, this is a very complicated history here. I'm not going to get too much into it. I think I'll mention Maxwell's equations in a little bit. We're studying light, but also electricity and magnetism. It's becoming a little more obvious that as we realize these things are somewhat related. The scientists who studied these things wrote the equations that explained our observations about electricity and light. They're called Maxwell's equations. And something interesting came out of those equations, and that was that the speed of light has to be constant for these observations to work, for these laws to work, which violates our understanding of relativity. As we mentioned earlier, just remember that when we talk about sound, if I were to run away from you while I'm talking to you, you would hear a change in the pitch of my voice because it would stretch the wave out and it would sound like my voice is getting lower. If I was running towards you as I was talking to you, that's if I'm fast and pretty fast, but you would hear the pitch go up. So we hear this with sirens and things that are this Doppler effect. That's what we expect, but with light we don't see that. If I had a flashlight and I was running towards you with it, you would measure the same speed of light as if I had a flashlight and I was running away from you with it. And again, that's true even if I could run really, really fast. If I was on a train or if I'm on a spaceship, whatever fast I'm going, the speed of light doesn't change whether I'm moving towards you or away from you. This is really different, and it couldn't be explained. So, like all science, we had to think of something. How can we possibly explain that? They came up with what's called the luminiferous ether, or the ether. This is often looked at as derisively in the history of science. Oh, how silly they were. How could they ever have thought this? Because there were so many problems with the ether. For it to be a medium to carry light, but not affect anything else. Because we don't see any impact of the ether on our own movement, on the movement of sound, or the movement of planets or anything else. Matter of fact, the experiment that sort of did away with it was just that if you think about how the ether would affect objects moving through it, there had to have been some detectable wind produced by the ether as objects large enough moved through it. The Earth should feel a slightly different wind from the ether as we moved through it in our revolution around the sun. And Michelson-Morley set up an experiment to test for this. Even an extremely slight wind. I mean, there had to be some, even if it was extremely slight, and they never could find it. Even at very, very fine measurements. They're still doing these kinds of experiments, still not finding it. Okay, there's no ether, there's nothing there. So, let me go back actually. So, if the ether is necessary to explain the speed of light being a constant, but there is no ether, it threw things into a pretty difficult situation. How can the speed of light be constant in an absolute reference frame? Because if there's no ether, that means there's nothing for that light energy to be moving through, to be propagated by. It's moving through a vacuum. It's moving without any need for a relative reference frame, so it's absolute motion. So this challenged physicists for a long time. Einstein's solution was his theory of special relativity. Basically, what the theory of special relativity says is that light is a constant in any reference frame. Now, again, if you read about this, it can get very confusing in terms of we're going to define reference frames differently. There are inertial reference frames and absolute reference frames. An inertial reference frame is one that, because we're all moving, for instance, with the Earth, we're in an inertial reference frame. Our inertia matches the Earth's inertia, so we're still relative to the Earth, moving relative to the Sun. That's what I mean by an inertial reference frame. So by stating that the speed of light is constant in all inertial reference frames, he was able to then mathematically devise not only the speed of light, but a few other things that we're going to see, and solve this problem. I'm not going to focus as much on the math, obviously, of relativity. I want to focus more on the ramifications that were pretty startling, pretty astounding. For instance, if this is true, you can't measure space and time separately from each other. You can't do it. And we've said this before, so this is our expectation today, but at the time this seemed really odd, that you can't measure distance and time without referencing the other. That meant that if you went close to the speed of light, if you could travel that fast, time would have to slow down. That prediction was really startling, right? How can time slow down? It would also mean that as you approach the speed of light, your mass would be contracted. You'd become smaller and smaller and smaller, and denser and denser and denser, right? So you would be approaching a black hole. You would be becoming a black hole if you accelerated yourself to the speed of light. Now that didn't bother people as much at the time because they weren't really thinking about actually trying to do that. Today we do. Today we think, well, what if we could go the speed of light? Right? It's in our science fiction all over the place. People are traveling the speed of light and faster. So how do we deal with these things? The time dilation has been dealt with in science fiction, again, from Planet of the Apes to any number of things where people have been put into hypersleep and then woken up, gone out in space, come back, and the Earth is thousands of years in the future, and they haven't aged but a few days, perhaps. Now that's true, that's real, that would be true if we could do that. If we could approach the speed of light and fly away from the Earth and then come back, your time on the spaceship would pass normally for you. On the Earth, watching the clock on the spaceship, it would appear to slow way, way down. So that by the time that people came back, a long time would, as a matter of fact, I'll show you in a little bit a demonstration of this. And that's been measured. We can actually measure that, that's true. Now, how do we overcome the other relativistic effects of our mass being compressed and becoming really dense? Science fiction spends less time worrying about that because, there must be a way. There must be a way to overcome that. We'll figure it out later. We'll just assume we will, and we'll go ahead and imagine traveling that fast. Yes?
So when the time on Earth slows down, as somebody traveling at the speed of light, their time would speed up, or?
It's the time on the spaceship that seems to slow down, or that slows down, essentially. Okay, so that a change in time for someone on the spaceship, a second for them would be a minute on the Earth, or however fast they're going relative to the speed of light. Okay, so again, this is relativity, and this is what makes this special relativity, because it's special only to light. It's only when we approach light speeds that this happens. You can sort of think of this, remember when we talk about Newton's laws, they work really, really well in our local reference frame. When we're measuring, when we're doing engineering on the Earth's surface, Newton's laws work because we're approximating the real world with such a small error that it's irrelevant. They only break down when you travel great distances, and that's we'll get to with general relativity, why Newton's laws don't work across great distances. We have to use Newton or Einstein's ideas. Same thing with special relativity. In normal everyday experience, we're never going to notice any of these relativistic effects. We're never going to be going fast enough to really notice this. But we do notice them when we look at things in space that are very far away, that have been traveling for a long time, or when we do think about what if we could travel this fast. So it's special in a couple senses. It's special because it only relates to light, but it's also somewhat special because it only relates to really extreme situations in the universe that we don't typically encounter. So again, we're talking about an ideal here, just like in Newton's laws, that works. It explains a lot, but we're not going to actually experience that reality very often. We're going to see a different range of things most of the time. Let me look at this, point out something else about this that I think is somewhat interesting. That's demonstrated by this cone. One of the things that comes up, and we'll look at, I have another slide that we'll look at this in a little more detail too, but when we talk about time being relative, all of a sudden, is that past and future, become somewhat relative. This cone sort of shows us at any given point, let's say this is where we are in the present, okay? Because of the speed of light, anything that happens here can only have causal influences within it's actually a sphere, not a cone, but it's easier to see this way, but within this cone. In other words, if something's going on out here, it can't possibly affect this event because it's too far away from light to get there that fast. So light controls time. Because the speed of light is slower than that, therefore this event cannot affect this event. I mean, if that's clear enough. Only things that happen within this cone can affect this event. Likewise, going into the future, this event can only affect things into the future that are within the future cone. Now, it may seem odd that we're talking about the speed of light and historical and future causation, But the reason we're doing this is because of all these paradoxes that the theory of special relativity presents to us, like the twin paradox, but also the grandfather paradox. If you go back in time, right, and you change your own fate by killing your grandfather, what does that do to you here, right? So this is like, well, wait, what? You know, what do you mean? If we can go back in time, if we could go back in time and kill our grandfather, we wouldn't exist here, right? Now, suppose if we go back in time, say out here, and change something, it's not going to affect the future, affect our present, because we're outside of that cone. So this is where this sort of becomes relevant. We're not traveling through time right now, but we think about these kinds of things in physics because, well, when we get far enough into it, with entropy and other concepts of how the universe has evolved and so forth, this does become an issue. There are considerations of time that would allow it to go forward and backward and things like that. We'll get to that when we get to the unifying theory. I don't want to get too far into that right now. But let's do consider some of these other paradoxes before we go forward, because this is really sort of what makes special relativity so interesting. Actually, I'll come back to this one. Let's look at this one. The twin paradox at first. Let me just go ahead and demonstrate. This is the one that, if I can get it to work, it depends on whether we have the shockwave plug-in properly. Oh, come on. I always hate it when they don't have these computers set up right. All right, well, maybe I won't be able to. Get it to work here. Let's see. As this is attempting to load, hopefully we'll get it. This Einstein's big idea was a NOVA series, and this is a really interesting website you might go to. Again, 1905 was when he came up with the theory of special relativity. 1915 is when he came up with the theory of general relativity. So we're in this sort of anniversary, centennial anniversary of Einstein's big ideas. This came out in 2005. 100 years after he devised special relativity. And let's try again. Come on. And next year will be 100 years from general relativity. If I can't get this to work, I'll just walk through, I'll just tell you what's supposed to happen using this picture. If you look at this little picture here, you'll see a spaceship, and on the spaceship is Captain Ein, and his twin brother Stein is staying on Earth. You can set how fast the spaceship can go relative to the speed of light, and what star it's going to travel to. These various stars are different light years away. And it will calculate for you the age of Captain Stein and his brother Stein after traveling to that system and coming back. And if you set the speed close to the speed of light and you go to a distant star that's many light years away, the difference in age goes from being a few days, years, to being centuries long, right? And these are real effects that we can actually watch. It's fun. Would have liked to have been able to show the actual applet work, but maybe we'll try again in lab next week or something like that. Now, the other thing that's on this slide, though, I mentioned that if this were following this theory of special relativity, as this spaceship approaches the speed of light, it's going to get smaller and smaller in length, more and more dense, and if it were to reach the speed of light, it would become a singularity. It would be just a very dense point in space, essentially a mini black hole. Now, if it came back and slowed down, what's going to happen? Is that contraction going to destroy all the information here, or is it going to be able to re-expand back out? Is that a relative to the person on the ground? Would the person in the spaceship still appear to see length and mass normally because their speeds are similar to light? We don't know all these answers. The other side to this, however, is that the speed of light appears to be the absolute fastest you can go, because if you get to that speed, you become a singularity, and that's it, right? I mean, that's as fast as you can go. It's as far as you can go. You can't go any faster. And so Einstein really insisted on this. The speed of light is the speed limit of the universe. You can't go faster. But people have been unsatisfied with this, like we are with any limitation. We don't want to be told we can't do something. So scientists and science fiction writers have been trying to figure out a way around this for a long time. And we're going to talk about one of the possible ways around this, or a couple of the possible ways around this in the next couple weeks. Traveling faster than light. Is that possible? Can we travel faster than light? There are two ways that I'll entertain. Well, maybe, two ways that I'll entertain that come from Einstein's ideas. When we get to general relativity, we'll focus more on wormholes. At this point, however, we might consider warp drives. I'll tell you how a warp drive works, theoretically. Theoretically, if you take the space around the ship, and instead of accelerating the ship, you accelerate the space-time itself, and the ship is kept in that sort of cocoon of space-time, so that within that space-time, normal relativity exists, but you can accelerate a wave of this space-time through space that can exceed the speed of light. Space-time itself could go faster. So the ship riding this wave could travel faster than the speed of light. That's theoretically how a warp drive works. Now, you can calculate how much energy this would take to actually accelerate that much space-time, and it's tremendous. I mean, it's more than we can conceivably produce. But theoretically, it's possible, yes?
Is that where some of the authors get the idea of space folding? Yes,
well, it's along those lines, yes. And we're going to come back to space folding a little bit when we talk about wormholes and general relativity in a minute. This is more like creating waves of space-time. One of the things, again, general relativity, when we get back to that, it predicts gravity waves, for instance, which we have recently measured, and things like that. So I'm going to come back to some of that. But the other thing that this special relativity does is that it tells us that energy and mass are the same thing, that E equals mc squared. Again, I'm not going to walk you through all of the derivations of these equations, but it comes directly from special relativity. And again, c is the speed of light. Energy equals mass times the speed of light squared. We do take advantage of this in nuclear reactions. C is a fantastically large number relative to our normal experience. The number here is not rounded off. Usually you see this rounded off, but 34,701,000,000 miles per second, miles squared per second squared. I mean, that's really fast, right? You don't usually see it in miles per second either, but that's pretty fast, right? We think of miles per hour as fast. This is miles per second, and it's 34,701,000,000 miles per second. So compared to that, our normal experiences are extremely small, which means even a very small amount of matter that is split apart can release a tremendous amount of energy. Right? So you take even a few atoms and you split them apart. The energy that's released is tremendous. This is why nuclear atomic bombs, nuclear energy power is really a lot of energy, but it's even with a very small amount of matter. It also works the other way. If you put it together, it releases a large amount of energy, and that's because the state of the energy state is lower in matter than separate. And again, I'm not going to go into a lot of detail with that, except that it would seem to violate our laws of conservation of energy that we studied earlier, which work for any other situation in which you're not converting mass and energy, but don't apply to this situation. All right. Let's go and get to general relativity. It's sort of hard to talk about one without the other, but Einstein didn't come up with this one until later. His theory of special relativity came about to explain things about light that couldn't be explained. Not only the speed of light, primarily the speed of light, but also the particulate nature of light and some other things. Again, Max Planck had already studied that, had already proven that light is made of particles. These particles are massless, however. They don't have any mass. But they are affected by gravity. So Einstein's thinking, okay, now I got to figure this out. I figured out how light can have a constant speed and what this means about the universe, and it explains a lot of things that we couldn't explain before. It's worked really well. Experiments have supported my theory. People are accepting it. This is great. But it also, now we have these new problems. If light doesn't have any mass, how can it be affected by gravity? I mean, I'll let that sink in for a second, because we always think of, weight, or your weight is the effect of gravity on your mass. We never think of gravity as affecting light, but according to special relativity it does, and we can observe that it does. So the way he explained that was to make space-time something, saying space itself is something, it's a fabric. This goes all the way back to Newton's idea of absolute versus relative relativity, and sides with Mach, actually, against Newton, in that the void, what we think of as a void, empty space, isn't empty completely. It isn't filled with an ether, but it is something. It is space-time. And space-time is curved by mass and energy. Since energy and mass are essentially the same thing, this makes sense, right? So E equals mc squared, we can see that not only does a massive object bend space-time, but so can energy. Energy and mass moving through space-time creates curves in space-time. Now this is really pretty astounding. In many ways even more astounding than special relativity. It explains gravity not as the way Newton sort of described the formula for it, which can calculate gravity, but explains it as momentum or acceleration of objects through this fabric of space-time. It predicts gravity waves. As I mentioned before, these have now been measured just recently by an experiment called LIGO, which has a component in Louisiana, so it's got a local connection. I'll show you a poster about this outside the lab at some point. That was a really big deal, and that was fairly recent. One of the earlier things that was observed that general relativity predicts is what's called gravitational lensing. And this is that just like any concave lens can bend light, curves in space can bend light. So you could see an object at a great distance, you'd actually see two images of the same object. This has been shown. So gravity is bending, or curved space is bending light in a way to create gravitational lenses. These have actually become very useful. Think of a telescope. A telescope has a lens in it, and it allows us to see farther distances. We can use gravitational lensing in the similar way to see things farther away. It's really pretty astounding what we can do with not only light telescopes, but X-ray telescopes and radio telescopes. Remember, all the different parts of the electromagnetic spectrum are available for these kinds of observations through different wavelengths. Now, one of the more interesting ones is that there is actually, according to general relativity, would be a delay in the effect of gravity. Let's say the sun disappeared all of a sudden. Now, as we've seen before, if the Earth disappeared, the moon would start moving in a straight line, right? So if the sun disappears, the Earth is going to start moving in a straight line. What Einstein predicted was that there would be a little bit of a delay there, that the Earth would continue to follow a curved path, even though the sun had already disappeared, because of the distance. Light cannot get from the sun to the Earth, so that curve doesn't immediately bounce back. It has a very slight time delay in the flattening out of that curve. The Earth would continue to follow that curve for a very short amount of time before it would then move in a straight line. And again, this has been observed. We can show this. These are astounding ideas, and again, I'm getting into more and more, I'm sort of getting deeper and deeper into some of these really counterintuitive, challenging ideas that are guiding modern physics and modern science. But most of you have learned completely opposite stories up to this point in all of your classes, right? Because we have to simplify things so much, and I want to give you this caveat. All of those things you've learned are not false. They're just true within limited ranges of relativity. What I'm talking about now is true, but we're only going to experience these things in a very broad sense of relativity. We're never going to see this on Earth. Okay? If the Earth disappeared, we would not see any time delay, because the masses are too small, they're too close together. We're only going to see this kind of thing in really big objects, like say a galaxy. Right? We can see this in a galaxy. Those are really, really big. They have a lot of gravitational effect and whatever. But we're not going to see this on everyday Earth. So what you learned wasn't wrong, it's just incomplete. It's within a smaller reference frame. It's like Newton's laws work within our reference frames, but if we have to send a spaceship to Saturn, we have to take relativity into account, because we can't just send it on a straight line. It's not going to get there, because it's going to actually follow curved space. It's not going to go in a straight line. Straight lines don't exist in outer space. This is one of those things Einstein had to use a different geometry to figure all this stuff out. Our Euclidean geometry that we use, that has flat planes and straight lines that are always parallel lines that never cross, those don't exist in the real world, in the real universe. You have to use a different geometry because everything is curved by mass and energy. It's really sort of mind-boggling, but it works, and it's allowed us to do a lot of really neat things. The redshift was predicted by general relativity before it was observed. And it's because of these gravitational effects, again, not because the redshift is a Doppler effect, not because the speed of light is changing, but because the effect of gravity on light over great distances shift it towards the red end of the spectrum if something is moving away. That was then observed and actually led to a pretty major step in cosmology. So in many ways, this theory was the birth of cosmology and the beginning of our connection of the very small to the very large in a fundamental way. From particles of light, photons, which we'll explain with quantum mechanics next week, to the biggest things that we see, galaxies and so forth. One of the other astounding things that general relativity predicted were black holes. And again, people were just like, that's just silly. Points in space that are so dense that not even light can escape? How could that be? That's just silly. Well, now we know that they're true or real. We can indirectly see them. I could show you some pictures. Now, one of the reasons you can't see a black hole directly is because there's no light coming from it. So what are you going to see? There are, however, streams of energy coming out, not of the black hole, but of the event horizon. Let me try to demonstrate this. I'll show this a little bit more closely. Again, I tried to find a single picture to talk about all the different aspects of a black hole. I couldn't really find a good one. This sort of gives me what I was looking for, though. If you look at the lines here, these are lines that are intended to show space-time, the fabric of space and time itself. And you'll see very similar lines in some other presentations I'll show you about string theory. And what you can see is that the lines are being bent, they're being curved quite dramatically. Because what they're showing is space-time is being curved by the mass that is the black hole. The black hole is actually an object. It'd be like taking all the mass in this room and squeezing it down into a very small little point. That'd be a very dense mass. This can only occur when there's enough mass to overcome the electromagnetic force, and all of the electrons flying around making things feel solid collapse in on the nucleus. And so there really is no space in between anything. All the mass is compacted down to the most dense state. Imagine now taking all of the mass in a galaxy and condensing it down into a small space. It may even be the size of a basketball or some larger amount, but it's the mass in the entire galaxy down into this small space. That's going to curve space-time a lot. And so it basically sits at the bottom of this well of space-time. What we call the hole is really the well that bends down to the black hole object. So the black hole is not the objects per se, but the well here, the hole in space. And it doesn't go through space. Well, we'll get to that if it could ever bend space enough to go through and create a wormhole. Right? This is where wormholes come from. But before that, let's look at at different points here, because all of the energy and mass in the area is being drawn in by this intense gravity and very rapidly going into the well. Now, if you look at a water in the bathtub trying to get down a drain, you'll see a little fountain coming out the top because it can't all go in that fast. So some of it gets pushed back out with a little spurt. Same thing happens with this energy. It's all trying to get in so fast, it can't all fit. And so you get a big stream of energy shooting out the top. This can be seen. This can be measured. This is what we can measure, we'll call quasars quite often. These black holes are rotating. Think of the original galaxy that collapsed, of course, was rotating. So the black hole is still spinning. And so if it's oriented at us the right way, we'll see this stream of energy come past us, and then again, and we can measure that rate, measure the rate of rotation of the black hole, its distance away from us, its mass. All of these things can be measured using that information. And we can see these things now. We can look at instances in space where black holes are forming, where they haven't gotten to this point where they're creating this much energy coming out. We can make black holes. We make them pretty much routinely. They don't last very long. The physics of a black hole is where we currently have some of our biggest challenges in physics because we can't really explain everything that's happening inside there. Some of you, I know one of you came to my office, we were talking a little bit about what Hawking has recently said about black holes. Stephen Hawking was the physicist who really sort of, it's not this simple, but proved the existence of black holes in many ways. He modeled them, he did the physics of them, he built his career on black holes and showing how they work and that they're real. We just recently sort of said, well, black holes don't exist because, not that they don't exist, but they don't exist the way we've described them because of the information going in being destroyed. All right, I'm not going to get into too much of that, but it's interesting how we're, I don't want you to feel like at any point, really, that I'm talking that we're at an end in our understanding of things. As our understanding grows, we ask more and more questions, we need more and more answers. One of the more challenging areas that we're trying to figure out right now is what's happening inside that well, at that point where that black hole is drawing all this material in. What's going on as that density reaches towards infinity? And there are a lot of possibilities of how this could play into a future Big Bang or multiple wormholes, all these other possibilities. That if we can figure out all this stuff, we might be able to do. We might be able to travel through them, through time, through space, maybe like Spock did in Star Trek from one timeline to another. Who knows? All right. I got to leave it there right now. We're going to come back to the physics of the impossible in our last lab. So we'll have a chance to talk about all these things when we do that. But let's get the quiz out of the way. And we'll come back to a lot of this stuff. Because hopefully what I've done is I've teased your imagination enough to then have a bigger conversation about all of these possibilities, what this might actually mean for us. All right. So question number 1. Einstein developed the theory of special relativity but not general relativity?
False.
That's false. Developed both ideas about a decade apart. Pretty astounding discoveries. General relativity describes gravity as the acceleration of space-time. This is true. Now, this is going to bring up a question of how do we reconcile this description of gravity with quantum mechanics? This is a major challenge. One of the problems with the black hole is that we're accelerating things to the speed of light into the black hole. What does that do to the information of the particles, the quantum particles, entering in there? And that's what Hawking was referring to in his latest announcement. So we have to be able to reconcile what's going on with the quantum world and the relativity, and we haven't been able to do that yet. Everything is relative? True. I would say that's true. I think more or less, that's what Einstein proved with general relativity, is that no motion is absolute. Everything is relative to something else. And this was a long-standing debate for a long time. We can explain gravity? No. We can describe it. We can model it. We can predict it. We can't say exactly how it works. Now, we have a couple different possible explanations, but we don't know that they're right, which one is right now, or whether what combination of the two explanations will turn out to be right. So we will talk about this next Thursday when we talk about string theory and loop quantum gravity and different ideas like that. Okay. And number 5, special relativity states that time slows down as you approach the speed of light.
True.
And that is true. Okay. All right, everything worked out? All right.
What was number 5?
True. True. Time does slow down as you approach the speed of light. Interesting phenomenon. Time is really an interesting concept. We're going to talk a lot more about time before this class is over. We're getting pretty close to this class being over. But not quite yet. But not quite yet. But not quite yet. But not quite yet.